Hello, in this video I'm going to be talking about continuous random variables. So let's first be clear on what I mean by a continuous random variable. In previous videos I've discussed discrete random variables, and I'm going to just use RV to abbreviate that. In a discrete random variable, we were able to look at the probability distribution by listing possible values for a random variable, x, and probabilities for each of those possibilities. So for instance, if a random variable x could take on values between 1 and 6, and the value was determined by the roll of a die, each of the probabilities would be 1/6, and the total of these probabilities we learned had to equal 1. So now we're looking at continuous random variables. So they're still random. We'll use something like a symbol x, but this time x can take on an infinite number of values. So the possibilities are limitless. So it's not going to work for me to create a table. I couldn't possibly list all the possible values of x. So we need another strategy. So I'm going to start by discussing one of the simpler probability distributions for a continuous random variable, and that will be a uniform continuous random variable. So we're going to look at the characteristics of this variable and its distribution. Alright, so a natural question would be, how would you know the type of distribution for a particular random variable, whether it's uniform or something else? So the way that you might investigate this, we're not going to be able to list single values for a continuous random variable, but you may recall from previous work that when we have a continuous variable or continuous data, it will sometimes create classes. So maybe something like from 0.1 to 10, and from 10.1 to 20, and so forth, 20.1 to 30, 30.1 to 40, and 40.1 to 50. And then, conduct an experiment many times, record our observations, and maybe we'll be able to come up with relative frequencies. So often we report these as a percentage. So, you would get a total of all your observations, and this would be a proportion for each of these classes. And then we can take the information in a table like this, and we can construct a histogram. And so, you might see something where we have various bars, one for each of the classes here, and the height of each bar corresponds to its relative frequency. And when we're finished, you may see something where the bars have a similar height. Now, they may not be exactly the same, so we give ourselves a little bit of leeway here, but these are roughly the same height, and so this might indicate to me that this is a uniform distribution. And so after I've investigated the type of distribution and determined that it's likely uniform, a natural question for me to ask is the range of the range of the possible values. So basically, I'd be looking along the horizontal axis here and saying, well, what are the endpoints that are covered in this relative frequency histogram? In particular, I'd be looking maybe at the lower class limit and the upper class limits. And in fact, those are the parameters that tell us pretty much everything we need to know about a uniform random variable distribution, a continuous uniform random variable distribution. A little shorthand notation: if we determine that a random variable does indeed follow a uniform distribution, I might say that the random variable x, and this symbol is the tilde, and we use it to say that this variable follows a certain distribution. In this case, I'll say a uniform distribution. You could say x is uniformly distributed, or x follows a uniform distribution, And the two parameters that I need to know, and I'll call them A and B, are the lower bound, and this would be the upper bound, on values, possible values, for my random variable x. So x can take on values any real number between a and b, and that may or may not include those in values a and b. All right, so in order to get a picture of what this looks like, we can draw a graph, and we'll put our lower bound here of a and our upper bound here of b. And so the graph that we use is called a probability distribution function, a PDF. And in the case of a uniform distribution, that graph is just a horizontal line that extends above this range of possible values. So this is a probability distribution function. And that's just an equation that helps us determine probabilities for outcomes in an interval for a continuous random variable. All right, so what happens outside of this range from a to b? So if it's not possible to get a value less than a, this probability drops down to 0, and that's what it remains for eternity as far as below a. And the same thing here, the possibilities above b are 0, and so this actually just drops down. So what we end up with is a rectangle shape, and that will be the shape for the graph of any uniform continuous random variable. So something to know about continuous random variables and their probability distributions. We equate area with probability. So in particular, the area under the graph, this is the of the PDF, the area under the graph and above an interval represents the probability, I'm sorry for that messy, that's probability that we will observe a value in that interval. Now, if the only possibilities for this distribution are values between a and b, then that means that the total area under this curve and over that interval has to be 1. There's a 100% chance that we're going to observe a value between a and b because those are the only possibilities, are values between a and b. So this area equals 100% or just 1.000. That's going to be the case. Now, the nice thing about this is, since the shape is a rectangle and I know the total area, I'll draw upon my geometry knowledge where area equals the length times the height. And it's going to be fairly easy for me to calculate this length. That's just b minus a. So the missing piece of information here is the height. I know that the area is 1, that length is b minus a, and so what would the height have to be? Well, we can just solve this by dividing both sides by b minus a. So the height of this curve, I'm calling it a curve in this case, it's actually this line, that horizontal line across, that height is 1 over b minus a. Now that's the, now let me say, if we wanted to find the probability associated with another interval within this range, so like a subinterval, let's say like from here to here, then we would just find the area under the curve and above that range. Luckily, we just end up with a smaller rectangle, And so now I know the height, that's going to be this consistent all the way across. So I would just need to know this length. So let's look at an example with some actual numbers and not just an A and a B there. So suppose that I have a continuous random variable. I'll just stick with x, and I let you know that it is uniformly distributed. So x follows a uniform distribution, and it has a lower bound of 7 and an upper bound of 15. And we want to just get a picture of what this distribution looks like. So I'll draw a horizontal number line and mark off 7 and 15. Since it's uniform, I know that there is a flat line for the probability distribution function that drops down to 0 at 7 and then at 15 again. And this total area is 1. Now the length of this side, so from here to here, would be 15 minus 7. In other words, 8. And I know that the total area under this curve is 1. And so that's going to allow me to solve for this height. So I know that 1 equals 8 times h. So if I divide both sides by 8, I know that this height is 1/8. So let's see, what is the probability that we would observe a value of x that is less than, let's say, 9. All right, so I'm going to add some other markers here. So halfway between 7 and 15 would be 11, and halfway between 7 and 11 would be 9. This would be 13, and there's 8, 10, 12, and 14. So less than 9. So I'm interested in the area that's under the curve and that's above that range. Well, less than 9 would be the same thing as saying that the probability of x is between 7 and 9 because that's the lowest possible value. So I'm looking for the area that's under the curve and above that interval. And so I've already found that the height of this shaded rectangle is 1/8, and it's easy to see that the length of this side is 2. So I can take 2 times 1/8, and that would be 2/8, which reduces to 1/4. And of course, if you prefer decimals, you could say that that's a 0.25, or if you prefer percentage, there's a 25% chance that we would observe a value of x between 7 and 9. Another example, what's the probability that x is greater than 12? So in this case, I'm looking for greater than 12, so that's over here. And the height I know is 1/8, and the length of this is 3, so that's 3/8. And even though I'm picking whole numbers here because it's easy for me to then do the calculations, this is a continuous random variable, and so we could certainly say what's the probability that x is less than 10.792 or something like that. 10.792, so I would want everything from here over. I would just need to take 10.792 and subtract 7 and then multiply that by an 1/8. Of course, you can also do some probability that x would take on a value between other numbers. So for instance, maybe between 8 and 14. So from 8 to 14, that 14 minus 8 is 6, and times the height of an 8, that would be 6/8 or 3/4. Now, a question that comes up naturally is, what's the probability that x takes on a particular value? Maybe 11. So 11 is just one value out of the infinite number of values between 7 and 15. So 11 is right here. And if we're thinking about what's the area that's under this curve and above this range? Well, the range, we're not actually given any range, we're given a particular value, so that just is a line which doesn't have any width, so 0 times 1/8 is 0. This probability is 0. With that in mind, when we look back up at our work above, I've been using strictly less than or strictly greater than. You could add or equal to any one of these. It wouldn't change a thing because allowing for the possibility that x would equal 8 or that x would equal 14 is just 0, so it doesn't change this probability from 3/4. Let's see. Oh, something else I'll mention quickly is if I said the probability that x was less than 20. Well, 20 is over here. Less than 20 would mean that x takes on a value, some value below 20. Well, all of the values that x takes on are below 20. There's a 100% chance of that. The probability that x would take on a value less than 6, that's 0. All of the values of x are between 7 and 15. There are no values. X never takes on a value less than 6. So since it never happens, that has a probability of 0. Alright, so I hope you'll join me for a follow-up video, and I'll do an example where we look at an application of the uniform distribution.